Something in deep space just forced Europe to do something it has never done before. And it wasn't a drill planned months in advance. Subscribe now, because what triggered this response is still unfolding. Just days ago, alerts began moving quietly through European space agencies, civil defense offices, and military coordination centers. The cause was an object designated 3I Atlas, formally catalogued as 3I Atlas. Within hours, Europe activated its largest planetary defense exercise ever attempted, involving multiple countries, real-time tracking systems, and emergency response simulations. Officials were careful with their words, but their actions said something else entirely. This report explains what 3I Atlas is, why the response was so fast and so serious, and what this unprecedented exercise reveals about how close humanity may already be to a real planetary threat. 3I Atlas first appeared as a faint, fast-moving object detected by the Asteroid Terrestrial Impact Last Alert System, the same global survey network that has previously flagged near-Earth objects with potential risk profiles. What immediately caught attention was not just its speed, but its trajectory. Unlike typical asteroids bound to the Sun, this object showed characteristics consistent with an interstellar origin, meaning it did not form in our solar system at all. Early orbital solutions calculated by teams working with NASA's Jet Propulsion Laboratory and the European Space Agency's Near-Earth Object Coordination Center showed a path that sliced through the inner solar system at an angle that demanded immediate refinement. As more data came in from observatories linked to the European Southern Observatory, the object's size estimates were revised upward, and its uncertainty corridor widened instead of shrinking. That alone raised concern. Normally, when astronomers refine an orbit, the margin of error collapses quickly. With 3I Atlas, it didn't. In fact, the more Europe observed it, the more scenarios remained open. That is the point where scientific curiosity turns into civil preparedness. By the time confirmations were cross-checked using legacy radar constraints derived from Arecibo data and optical tracking pipelines connected to the Vera Rubin Observatory, Europe had a choice: wait and watch. Or test everything. They chose the second option. What followed was not a press event or a symbolic tabletop exercise. It was a live, multinational simulation designed to stress-test Europe's ability to detect, communicate, and respond to a fast-moving celestial threat with limited warning. Airspace coordination, satellite tasking, emergency communications, and scientific command chains were all activated simultaneously. This was not about panic. It was about timing. According to analysts familiar with ESA procedures, the trigger threshold was crossed when models showed that if 3I Atlas had been on a slightly different inbound vector, the warning time could have dropped below weeks. That is dangerously short by planetary defense standards. And here is the part that matters most. Europe did not run this exercise because impact was predicted. They ran it because uncertainty was too high. Interstellar objects are rare. Only a handful have ever been confirmed, and each one rewrites assumptions about how material moves between star systems. Researchers at the Harvard-Smithsonian Center for Astrophysics have long warned that interstellar bodies may carry extreme velocities, unfamiliar compositions, and unpredictable structural behavior. Unlike typical asteroids, they don't follow rules we are comfortable with. As tracking continued, Instruments aboard space telescopes, including follow-up scheduling windows coordinated with the James Webb Space Telescope, were evaluated, not to image the object in detail yet, but to determine whether thermal signatures or outgassing behavior suggested instability. Nothing dramatic was observed, but nothing reassuring either. This is where the problem deepened. 3I Atlas did not behave like a clean, inert rock. Subtle changes in brightness hinted at surface activity, possibly driven by materials never before exposed to our Sunday. That meant models based on familiar comets or asteroids could not be trusted fully. And when you cannot trust the model, you train for the worst case. Europe's planetary defense drills simulated everything from delayed detection to fragmented impact scenarios. Emergency managers were forced to respond as if the object's nature could change mid-approach. Communication delays between observatories, governments, and civil agencies were intentionally introduced to test resilience. Quietly, efficiently, and without drama, Europe treated 3I Atlas as a rehearsal for something bigger. And this raises a question that scientists are only beginning to ask out loud. If this object alone was enough to trigger the largest planetary defense exercise in European history, what happens when the next one arrives with less warning? As soon as the alert around 3I Atlas was circulated, the response across Europe was not symbolic or academic. It was operational. Within hours, coordination channels between space agencies, civil protection authorities, and defense planners were activated. This was not a press exercise. It was a stress test of how quickly the continent could react if the numbers moved from theoretical to real. The object itself, 3I Atlas, had already been on tracking lists for some time, monitored by automated sky surveys feeding data into shared European and international systems. Facilities tied to the European Southern Observatory and data streams from legacy Arecibo observations were already contributing orbital refinements. What changed everything was the latest update, a narrowing uncertainty window combined with new brightness behavior that suggested either fragmentation or a change in surface activity. At that point, the conversation shifted. This was no longer just about where the object might be in 6 months. It became about what would happen if it wasn't where models expected it to be. Planetary defense is often misunderstood as a single dramatic action, like launching a missile into space. In reality, it's a layered process built around time. Detection buys time. Tracking buys clarity. Clarity buys options. And Europe's exercise was designed to test exactly how much time it truly had. Engineers at the European Space Agency began cross-checking orbital solutions with independent pipelines, comparing outputs against models from NASA's Jet Propulsion Laboratory and simulations run through the Harvard-Smithsonian Center for Astrophysics. The Vera Rubin Observatory, although still in its early operational phase, was also factored into forward-looking planning because its survey cadence will redefine early detection in the coming years. What made this drill unprecedented was that it did not assume a clean outcome. Scenarios included partial fragmentation, unexpected acceleration from outgassing, and even the possibility of non-uniform density factors that have historically caused small but critical errors in prediction. Scientists still remember how comet behavior surprised observers during previous close solar passes, recorded by Hubble's spectrograph data and later confirmed by Keck Observatory follow-ups. Civil authorities were looped in next, not because impact was imminent, but because communication failure is often more dangerous than physical risk. Emergency planners reviewed how information would be released to the public, how false rumors would be handled, and how to avoid panic without hiding facts. This is where lessons from previous natural disasters were quietly applied. Behind closed doors, one uncomfortable question kept resurfacing. If 3i Atlas changed its behavior tomorrow, would anyone know fast enough? That question drove the heart of the exercise. Simulated updates were injected into the system, small deviations, subtle changes in velocity, unexpected brightness spikes, and teams were forced to respond in real time. Some responses were fast. Others exposed bottlenecks that had never been visible on paper, and that's when the drill did its real job. It revealed that planetary defense is not just a space problem, it's a coordination problem, a data sharing problem, a decision-making problem under uncertainty, the kind of problem that only shows itself when the clock is ticking. By the end of the first phase, one thing was clear to everyone involved. 3i Atlas did not need to be on a collision course to justify concern. The uncertainty alone was enough. And that realization set the stage for what came next, when planners began asking not whether Europe could respond, but whether the world could respond together if the next update crossed a line no one wanted to see. What changed everything was not panic, but procedure. Within hours of the 3i Atlas alert, Europe did not issue public warnings or dramatic statements. Instead, something quieter and far more serious began. Secure channels lit up between observatories, space agencies, and civil defense planners. This is the part most people never see. Long before headlines appear, there is a choreography that has been rehearsed for years. At the European Space Agency's Space Situational Awareness Program, analysts pulled historical orbital data and began stress testing assumptions. The goal was not to predict an impact, but to answer a harder question. If this object behaved unexpectedly, how quickly could Europe understand that change and respond? Facilities tied to the European Southern Observatory cross-checked astrometric measurements from ground-based telescopes in Chile and the Canary Islands. These were paired with data streams from space-based sensors, including infrared tracking methods originally developed for near-Earth objects, but now adapted for interstellar trajectories. The object's speed, its unusual brightness profile, and subtle variations in its coma did not fit neatly into standard comet models. At the same time, researchers at the Harvard-Smithsonian Center for Astrophysics and collaborators at ESA were quietly consulted, not for alarmist interpretation, but for statistical context. How often do objects like this appear? How often do their early parameters change after initial detection? The answer was uncomfortable. Interstellar objects are rare enough that every new one sits on the edge of what models can confidently explain. This is why the planetary defense exercise expanded so quickly. What Europe activated was not a single drill, but a layered simulation. Detection timelines were compressed. Communication chains were tested under artificial delays. Decision makers were forced to act with incomplete information, mirroring real conditions. The exercise assumed no impact was guaranteed, but also assumed that waiting for certainty would be a mistake. At the European Commission's Emergency Response Coordination Centre, scenario planners introduced cascading effects. What happens if orbital updates shift by fractions of a degree? What if public misinformation spreads faster than verified updates? What if satellite infrastructure must be protected from debris or electromagnetic interference tied to a close solar interaction? This is where planetary defense stops being abstract science and becomes logistics. Power grids, navigation systems, and satellite constellations were introduced into the simulation. Not because 3I Atlas was expected to strike Earth, but because history has shown that near misses can still disrupt technology. The Carrington event is often mentioned in this context, but more recent, smaller solar particle events have already forced satellite shutdowns and rerouting of flight. ESA's coordination with national agencies reflected those lessons. Meanwhile, astronomers continued watching the object itself. Spectral data hinted at volatile behavior that did not evolve smoothly over time. Some readings suggested rapid surface changes, others showed relative stability. This inconsistency was one of the main reasons the drill escalated. When models disagree, preparedness becomes the only safe response. At NASA's Jet Propulsion Laboratory, orbital analysts shared non-classified trajectory refinements with European counterparts. These exchanges are routine, but the speed mattered. Even tiny deviations in interstellar objects carry outsized uncertainty because they arrive from directions and velocities that our long-term datasets barely cover. The Vera Rubin Observatory, although not yet fully operational for survey work, was referenced repeatedly in planning documents. Its future role loomed over the exercise as a reminder. This will not be the last time humanity encounters something like this. The question is not if, but how prepared the systems will be when it happens again. What made this exercise different from previous ones was not fear of impact, but fear of surprise. The working assumption shifted from can we deflect it to can we understand it fast enough. That distinction matters. Deflection requires years of planning. Understanding requires days or even hours. The drill forced agencies to practice rapid interpretation, not just response. By the time the exercise entered its later stages, the conclusion was already forming among planners. 3I Atlas was unlikely to threaten Earth directly, but it had already done something more important. It exposed gaps, delays, and assumptions that had gone untested under truly unfamiliar conditions. This is the quiet reason Europe took the alert seriously. Not because disaster was imminent, but because uncertainty was real, and uncertainty in space has a way of arriving without warning. The final phase of the drill focused on communication. How much information should be shared publicly and when? How do you explain interstellar uncertainty without feeding panic? Scientists from institutions like ESO and policy advisors worked side by side, drafting messages that were accurate, restrained, and adaptable as data evolved. By the end of the exercise, one conclusion stood out above all others. Planetary defense is no longer just about asteroids on predictable paths. It is about rare objects, unusual physics, and the speed at which humanity can turn observation into understanding. 3I Atlas did not need to hit Earth to change how Europe thinks about space threats. It only needed to appear, and next time, there may be less time to practice. Across Europe, that urgency didn't come from panic or rumor. It came from data. As soon as 3I Atlas was flagged as a high-interest interstellar object, the first calls weren't political. They were technical. Analysts at the European Space Agency's Near-Earth Object Coordination Center in Frascati began pulling trajectory updates directly from global observatories, comparing them against long-term impact probability models that had been refined after past near-miss events. This wasn't the first time Europe had rehearsed planetary defense, but it was the first time those rehearsals were triggered by an object that did not originate inside our solar system. That distinction matters more than most people realize. Objects born within our solar system, typical asteroids and comets, follow paths shaped over billions of years by the sun and planets. Their behavior is familiar. Their compositions are often predictable. But an interstellar object like 3I Atlas arrives with a history written somewhere else, under different stars, influenced by physics we didn't observe and forces we didn't track. That uncertainty alone is enough to elevate risk. Within hours, ESA began coordinating with NASA's Jet Propulsion Laboratory, which maintains the most comprehensive orbital databases on potentially hazardous objects. JPL's Sentry system, designed to assess impact probabilities decades into the future, was recalibrated to account for 3I Atlas's unusual velocity profile and non-gravitational forces, subtle accelerations that can arise from outgassing, fragmentation, or structural instability. Those non-gravitational effects are notoriously difficult to model. Even a tiny change in mass distribution can shift a future trajectory by thousands of kilometers. This is why Europe moved quickly. The planetary defense exercise wasn't about predicting an impact tomorrow. It was about stress testing every layer of response, detection, communication, decision-making under conditions of uncertainty. In Germany, Italy, France, and Spain, emergency response agencies were looped into simulated data feeds. These feeds mimicked real-time updates from telescopes like the European Southern Observatory's Very Large Telescope in Chile and radar constraints derived from legacy Arecibo datasets. Each update slightly altered the projected close approach corridor, forcing teams to reassess risk maps again and again. The goal wasn't speed alone, it was adaptability. Meanwhile, scientists at the Harvard-Smithsonian Center for Astrophysics were reviewing spectral data tied to 3I Atlas, looking for clues about its composition. Early analysis suggested an unusually dense nucleus compared to most long-period comets, raising questions about how it would behave if subjected to solar heating or tidal stress. Density matters in planetary defense. A porous rubble pile behaves very differently from a compact, monolithic body. Fragmentation could reduce impact risk or multiply it. At the same time, radio astronomers revisited archival observations. Stanford researchers familiar with Ronald Bracewell's early work on interstellar probes emphasized caution in interpretation, reminding teams that unusual signatures don't imply intent, only unfamiliar physics. Still, the exercise pressed forward. One scenario simulated a slight but measurable acceleration as 3I Atlas passed perihelion, forcing recalculation of its post-solar trajectory. Another explored communication delays between observatories and civil authorities, highlighting how even a few hours of lag could cascade into confusion. In Brussels, policymakers weren't asked to make dramatic decisions. They were asked to listen, to understand how scientific uncertainty translates into real-world risk management. This is the quiet reality of planetary defense. Most of the work happens long before headlines. And beneath it all was a simple question driving the exercise forward, not whether 3I Atlas would strike Earth, but whether humanity was ready to respond coherently if the unexpected happened. Because in space, the unexpected is the rule, not the exception. As more details came in, what made the response unusual wasn't just the size or trajectory of 3I Atlas. It was the speed at which institutions reacted. Within hours of the initial alert, agencies that normally operate quietly in the background moved into public coordination. The European Space Agency confirmed that its Near-Earth Object Coordination Center began cross-checking orbital solutions using independent data streams pulling from observatories in Spain, Italy, and the Canary Islands. At the same time, data from the Vera Rubin Observatory's early survey runs were quietly reprocessed to look for any missed pre-discovery images that might extend the object's observation arc. This matters because the longer an object is tracked, the more accurately its future path can be predicted. Short observation windows leave room for uncertainty, and uncertainty is exactly what planetary defense planners are trained to eliminate. Engineers at ESA's Space Situational Awareness Program ran thousands of Monte Carlo simulations, not because an impact was expected, but because the margins were wider than normal for an object already classified as interstellar. 3I Atlas didn't behave like most long-period comets. Its inbound velocity was higher than typical solar system bodies, consistent with an origin beyond the Kuiper belt and Oort cloud. That alone placed it in a rare category previously occupied by only a handful of known objects, including Oumuamua and Borisov. But unlike those earlier visitors, 3I Atlas showed subtle deviations in its motion that could not be fully explained by standard outgassing models. At NASA's Jet Propulsion Laboratory, orbital dynamicists examined non-gravitational acceleration terms, the same type of analysis used during the Oumuamua investigation. Hydrogen, carbon monoxide, and carbon dioxide sublimation were all tested as possible causes. None of them cleanly matched the observed changes. The forces were small but persistent, enough to widen future position estimates by thousands of kilometers over time. That widening uncertainty is what triggered the next step. Across Europe, emergency preparedness agencies were briefed not on impact scenarios, but on communication protocols. How quickly could information be shared between civilian governments, military tracking systems, and scientific institutions if probability thresholds changed? This was not a drill announced after the fact. It was a live exercise unfolding alongside real data, with simulated branches added only to stress test decision chains. At the European Southern Observatory, astronomers prioritized telescope time to capture high-resolution spectroscopy of the coma. Early results suggested a composition richer in volatiles than expected for an object that had already survived close stellar environments before entering our system. Some spectral lines hinted at complex organic molecules, the kind often associated with early solar system chemistry, but seeing them in an interstellar object raised difficult questions about how common such chemistry might be beyond our neighborhood. Meanwhile, the James Webb Space Telescope was quietly tasked with infrared observations, not to look for danger, but to measure thermal behavior. How fast was the surface heating? How evenly was heat distributed across the nucleus? Uneven thermal response can reveal internal structure, fractures, or voids that affect how an object reacts to solar radiation. Early infrared maps showed temperature gradients sharper than models predicted, suggesting the surface was not uniform. None of this meant catastrophe, but it did mean unpredictability. Planetary defense isn't only about stopping impacts, it's about understanding unknowns before they become emergencies. Europe's drill tested how fast scientists could move from observation to interpretation and how quickly policymakers could be brought into that loop without distortion or panic. The exercise simulated press, leaks, conflicting interpretations, and public misinformation, all while real scientists continued refining orbital data in real time. One detail that stood out to analysts was timing. The drill began earlier in the object's approach than usual. Historically, large-scale planetary defense exercises are conducted when an object's path is already well constrained. In this case, authorities chose to act while uncertainties still existed. That choice reflected lessons learned from past near misses, including Apophis, where early ambiguity drove public anxiety years before clearer data emerged. As the days passed, 3I Atlas continued inward, and with each new observation window, the margins narrowed slightly but never disappeared. It remained a low-probability threat, yet a high-interest case study. Harvard-Smithsonian researchers noted that interstellar objects may represent a blind spot in current planetary defense frameworks, which were largely designed around solar system dynamics. The drill expanded accordingly. Scenarios now included communication with international partners beyond Europe, data sharing with NASA's Planetary Defense Coordination Office, and cross-verification with radio observatories using legacy Arecibo data patterns adapted for optical targets. Even Voyager 1 telemetry was referenced indirectly as a reminder of how little direct sampling we have of interstellar material. At no point did officials claim an imminent impact. What they acknowledged, carefully, was that 3I Atlas was forcing systems to confront edge cases. Objects that arrive fast, behave oddly, and carry chemical signatures formed far from our sun challenge assumptions baked into decades of models. And that is why Europe treated this moment seriously. Not because disaster was expected, but because uncertainty was real, measurable, and moving closer by the day. As the alerts around 3I Atlas began circulating through European space agencies, what made this situation different from past asteroid briefings wasn't the size alone, or even the trajectory. It was the timing. 3I Atlas entered the inner monitoring window during a period when multiple planetary defense systems across Europe were already in testing phases. Instead of postponing, authorities chose to escalate. At ESA's Space Operations Center in Darmstadt, Germany, analysts began running real-time simulations using updated orbital data shared by NASA's Jet Propulsion Laboratory and the European Southern Observatory. The object's path was refined using cross-checks from ground-based observatories, including early input from legacy Arecibo radar models and newer optical tracking data, feeding into ESA's Near-Earth Object Coordination Center. What raised concern wasn't a confirmed impact scenario, but uncertainty margins that refused to shrink as fast as expected. Normally, as more data comes in, prediction cones tighten. With 3i Atlas, those cones remained stubbornly wide. Minor variations in solar radiation pressure, outgassing behavior, and rotational state were producing measurable divergence in projected paths. That alone was enough to trigger protocol reviews. At the same time, the Vera Rubin Observatory's pre-survey simulations were referenced to test how quickly such an object could be rediscovered if it slipped behind solar glare. The answer was uncomfortable. In some models, 3i Atlas could temporarily vanish from optical tracking at the worst possible moment, only to reappear with limited warning. This is where Europe's response shifted from academic to operational. Instead of treating the object as a distant theoretical risk, ESA activated a full-scale coordination drill involving civil defense agencies, satellite operators, and emergency planning units across multiple countries. France, Germany, Italy, and Spain all participated. Communication, latency, data sharing speed, and decision hierarchies were stress-tested as if an actual impact probability update were imminent. Publicly, officials were careful with language. No impact was announced, no evacuation plans were mentioned, but internally, the exercise was framed around a simple question. If this were real, are we ready? Part of the drill focused on satellite vulnerability. Engineers referenced past solar storm interference cases and compared them with model debris fields that could result from a fragmented interstellar object. Even a non-impacting pass could generate cascading risks if fragmentation occurred near key orbital lanes. Data from Voyager 1's historic dust measurements was briefly referenced as a baseline for how small particles can behave unpredictably in heliospheric conditions. Meanwhile, astronomers at the Harvard-Smithsonian Center for Astrophysics weighed in on composition models. Early spectral readings suggested a mix that didn't align cleanly with typical long-period comets. That didn't mean artificial, but it did mean unfamiliar. And unfamiliar objects are harder to predict. Throughout the drill, one phrase kept surfacing in internal briefings: decision time compression. The fear wasn't a single catastrophic event, but a scenario where warnings arrived too late for coordinated action. 3i Atlas became the test case for that fear, and that is why Europe didn't wait. They didn't wait for certainty. They didn't wait for headlines. They treated ambiguity itself as the threat. What makes this moment different from past asteroid alerts is not just the size or speed of 3i Atlas, but the timing. Europe's response did not happen in isolation or after months of quiet analysis. It happened fast. Within days of the updated trajectory data being circulated through international monitoring networks, emergency coordination channels were activated across multiple European agencies. This wasn't public panic. It was silent preparation. The first signals came through the same systems designed to catch objects long before they become a threat. Observatories linked to the European Southern Observatory and data feeds shared with NASA's Jet Propulsion Laboratory began flagging unusual parameters. 3i Atlas was not behaving like a typical near-Earth object. Its orbital uncertainty range narrowed rapidly, but instead of calming analysts, it raised new questions. The probability of impact remained low, but the margin for error shrank enough to trigger procedural thresholds that had rarely been tested outside simulations. At ESA's Near-Earth Object Coordination Center in Italy, analysts began running high-resolution models, combining optical data, infrared readings, and legacy datasets pulled from Arecibo's archived radar observations. What they were looking for wasn't confirmation of an impact, but confidence in what the object was, how it moved, and how reliably its future position could be predicted, and that confidence wasn't coming easily. One of the reasons 3I Atlas drew such intense scrutiny is its classification history. Initially logged as a routine discovery, later re-examined as potentially interstellar, its path did not neatly align with long-period comets from the Oort cloud. Data comparisons made with help from the Harvard-Smithsonian Center for Astrophysics suggested its velocity relative to the Sun was unusually high. Not unprecedented, but enough to place it in a small and closely watched category. As this data circulated, Europe quietly escalated. Civil protection agencies in several countries were notified under non-public protocols. Military space tracking units were asked to contribute independent observations. Universities tied into the Vera Rubin Observatory's upcoming survey models were consulted to stress test assumptions. This wasn't fear, it was redundancy. The planetary defense drill that followed was the largest Europe had ever conducted, not because 3I Atlas was expected to hit, but because it provided a rare real-world scenario complex enough to test the entire chain. Detection, verification, communication, decision-making, public response, each step was run as if time mattered, because one day it will. Inside the exercise, hypothetical branches were explored. What if the object fragmented? What if non-gravitational forces, like asymmetric outgassing, altered its path? What if a late discovery reduced warning time to weeks instead of years? These weren't science fiction questions. They were pulled directly from known asteroid behavior documented by missions like NASA's DART experiment and tracked through Hubble spectrograph records. What became clear during the drill is how fragile modern infrastructure can be in the face of even a small probability event. A strike in an uninhabited area could still disrupt satellites, power grids, and global communications. That reality shaped Europe's urgency. Planetary defense is no longer just about impact avoidance, it's about resilience. And through all of this, 3I Atlas continued its silent journey. No alarms, no visible changes to the naked eye. Just a distant object, millions of kilometers away, quietly forcing governments to rehearse for a future they hope never arrives. What pushed this from a routine tracking notice into a continent-wide response was not panic, but timing. 3I Atlas was not discovered at a comfortable distance. It appeared already deep inside the inner solar system, moving faster than most long-period objects normally do at that range. When analysts at the European Space Agency's Near-Earth Object Coordination Center in Frascati began running refined orbital solutions, they noticed something unsettling. The margin for error was shrinking faster than expected. Small uncertainties in velocity, when projected forward, created very different future paths, some harmless, some uncomfortably close. This is where people often imagine alarms going off and politicians being briefed in dark rooms. In reality, the response began quietly, inside software. Orbit determination teams fed fresh observations from the European Southern Observatory in Chile, including data from the Very Large Telescope, into updated models. At the same time, independent measurements from the Pan-STARRS survey and follow-up photometry cross-checked brightness changes. The goal wasn't to confirm an impact, it was to answer a more basic question. How stable is this object's motion? The answer was not reassuring. 3i Atlas showed subtle deviations from a purely gravitational path. Nothing dramatic, no sharp turns, no impossible accelerations, but enough to suggest that outgassing, thermal stress, or internal fragmentation could be influencing its trajectory. Similar effects have been seen before, notably with Comet 67P studied by ESA's Rosetta mission, but the scale here was different. The activity seemed asymmetrical. One side of the object brightened faster than models predicted, while the opposite side remained oddly inert. This matters because even a tiny thrust, sustained over weeks, can shift an object's future position by thousands of kilometers. That is when the discussion moved from tracking to preparedness. Europe's Planetary defense framework is designed to avoid last-minute decisions. Under ESA protocols, any object with uncertain behavior and potential Earth-crossing geometry triggers simulation exercises, not public alerts. These drills are meant to stress-test coordination, not scare the public. 3i Atlas met that threshold. Within days, agencies across Europe were looped in. Civil protection authorities in Italy, Germany, France, and Spain participated in tabletop scenarios. Not because an impact was predicted, but because communication delays, data handoffs, and decision timing needed to be tested under realistic conditions. At the same time, scientists at the Harvard-Smithsonian Center for Astrophysics and NASA's Jet Propulsion Laboratory were independently reviewing the same data sets. This wasn't a European-only concern. Planetary defense is inherently global. No telescope sees everything, and no model is trusted unless it survives scrutiny from multiple teams. One particularly interesting detail emerged from thermal modeling work shared between JPL and ESA researchers. As 3i Atlas approached perihelion, the side facing the Sun heated rapidly, but infrared signatures suggested heat was not diffusing evenly through the nucleus. That implies internal layering, possibly a rubble pile structure with voids, or regions of different composition bonded weakly together. If true, that would explain the observed coma growth fluctuations and the irregular brightness curve recorded by the Hubble Space Telescope's spectrograph. It would also mean the object's future behavior could change suddenly, without warning, if internal stresses cause partial breakup. This is the nightmare scenario for prediction models, not because it guarantees danger, but because it limits certainty. So the drills continued. ESA's planetary defense teams simulated response timelines, how quickly new observations could be integrated, how fast orbital updates could be issued, and how clearly uncertainty could be communicated to governments without exaggeration. The exercise deliberately included worst-case communication failures, delayed telescope time, conflicting data, and media leaks, all to see where the system bends or breaks. And through all of this, one fact remained consistent. No one was saying an impact was imminent. What they were saying, quietly and precisely, was that 3i Atlas was not behaving like a simple, inert space rock. And in planetary defense, uncertainty itself is a risk that must be managed. As the object continued its journey, more data would arrive. The question was whether those data would narrow the future or open it even wider. Across Europe, what makes this moment different is not panic, it's procedure. When alerts tied to 3i Atlas began circulating through monitoring networks, they didn't land on social media first. They landed on desks inside observatories, space agencies, and civil protection offices. At the European Space Agency's Space Situational Awareness Program, analysts compared orbital updates coming from multiple sources at once: optical surveys, infrared tracking, and radar estimates shared through long-standing coordination channels. The data wasn't screaming impact. It didn't need to. What mattered was uncertainty. 3i Atlas sits in a category that planetary defense planners watch very closely. Objects that are not immediately threatening, but not comfortably predictable either. Its trajectory solutions showed widening error margins the farther forward scientists projected them. That doesn't mean danger tomorrow, it means planning today. This is exactly the scenario Europe has trained for on paper for years, but rarely rehearsed at scale. Within hours, simulated briefings began moving between ESA headquarters, national space agencies, and emergency planning departments. Italy, Germany, France, and Spain activated tabletop exercises designed to test response speed, not evacuation orders. The goal was coordination, how fast data moves, how clearly it's communicated, and how consistently different nations interpret the same scientific inputs. At ESA's Near-Earth Object Coordination Center in Frascati, teams leaned heavily on observation data coming from the European Southern Observatory and the Vera Rubin Observatory's early survey simulations. The Rubin facility, though still preparing for full operations, has already reshaped how scientists think about object discovery cadence. Instead of rare detections, the future brings constant updates, and that changes decision-making pressure. 3i Atlas became a test case, not because it was confirmed dangerous, but because it exposed how modern planetary defense works in reality. Slow, methodical, and deeply human. Scientists debated assumptions. Engineers questioned sensor biases. Policy advisors asked uncomfortable but necessary questions about thresholds. At what probability does preparedness become action? Meanwhile, on the other side of the Atlantic, NASA's Jet Propulsion Laboratory quietly shared refined orbital solutions derived from combined telescope datasets and historical modeling frameworks developed after earlier close approach events. This kind of cooperation isn't new, but the scale is. Planetary defense is no longer theoretical. The drills unfolding across Europe were designed to stress communication chains more than technology. Could a mayor understand what a 1 in 10,000 probability corridor actually means? Would news agencies distort cautious language into alarm? Could scientific nuance survive a 24-hour media cycle? These questions mattered as much as the asteroid itself. In parallel, radar specialists referenced legacy datasets from Arecibo, not because the observatory still operates, but because its archived measurements remain a gold standard for modeling how irregular objects behave under gravitational stress. 3i Atlas, with its unusual brightness variations and apparent structural complexity, fit the profile of bodies that don't always follow clean equations. That doesn't mean it's artificial, it means it's complicated. Comets and interstellar objects often behave in ways that challenge first impressions. Outgassing jets can subtly alter trajectories. Fragmentation events can change reflective properties overnight. The James Webb Space Telescope has already shown how misleading size estimates can be when based solely on visible light. That's why Europe's response wasn't dramatic, it was deliberate. This exercise wasn't about stopping an asteroid. It was about proving that dozens of countries could interpret evolving science the same way at the same time without confusion. That's the real defense. Because if one day an object does move from unlikely to possible, the hardest part won't be physics. It will be trust. Trust between scientists, governments, and the public. And 3i Atlas, quietly passing through the inner solar system, has already done its job. It reminded Earth how fragile certainty really is and how preparation begins long before danger ever arrives. The reason Europe reacted so quickly is not panic, it is memory. Across ESA briefing rooms and national space agencies, there is a quiet understanding that objects like 3i Atlas do not give long warnings. They do not announce intent. They arrive, and by the time certainty forms, the window to act is already closing. 3i Atlas was not first spotted by a dramatic telescope photo or a press release. It appeared as a faint anomaly in wide-field survey data, the kind that software flags first and humans argue about later. Initial detection pipelines tied to the European Southern Observatories survey networks and cross-checked with data streams from the Vera Rubin Observatory flagged it as unusual not because of size alone, but because of motion. Its trajectory did not fit neatly into known comet families. Its velocity suggested an origin far outside the solar system, something supported by follow-up orbital solutions refined by analysts at NASA's Jet Propulsion Laboratory. When orbital models were tightened, a new concern emerged. The uncertainty corridor, the zone where the object could plausibly travel, overlapped with Earth's orbital neighborhood more closely than expected. Not a predicted impact? Not yet, but close enough to force planning. This is the part that rarely makes headlines. Planetary defense is not about predicting doom. It is about rehearsing uncertainty. Within hours of confirmation, the European Space Agency initiated coordination calls with national emergency planners, satellite operators, and defense ministries. This was not because 3i Atlas was confirmed to be dangerous, but because Europe had never before tested a full-scale response to an interstellar object with limited historical data. Unlike near-Earth asteroids catalogued for decades, 3i Atlas arrived with no long observational arc, no old photographs, no ancient light curves, just weeks of data and a lot of unknowns. At ESA Space Operations Center in Darmstadt, simulation teams began running parallel scenarios. One assumed a harmless flyby. Another modeled a fragmentation event under solar heating. A third explored worst-case deflection requirements if late changes in trajectory occurred. Each scenario pulled from lessons learned during previous exercises like the Hera and DART mission collaborations, where scientists practiced nudging asteroids to test humanity's ability to alter cosmic paths. But this time, the object was not cooperative. Unlike typical asteroids, 3I Atlas showed signs of structural instability earlier than models predicted. Observatories using the Keck telescopes in Hawaii detected irregular brightness fluctuations, not the smooth periodic changes expected from a rotating rock, but chaotic spikes suggesting active outgassing or surface disruption. Meanwhile, spectrographic data compared against Hubble's historical comet records revealed chemical signatures that did not line up cleanly with known comet classes. None of this meant danger, but it meant ignorance. And ignorance is the one thing emergency planners cannot tolerate. So Europe activated its largest planetary defense drill to date. Airspace agencies practiced satellite protection protocols, simulating radiation storms and debris risks. Power grid operators rehearsed geomagnetic disturbance responses, drawing on models from the Harvard-Smithsonian Center for Astrophysics that study how solar and cosmic events interact with Earth's magnetosphere. Civil defense teams tested communication chains designed to move from scientists to governments to the public without distortion or delay. What made this drill different was that it unfolded in real time alongside real observations. As 3I Atlas continued its approach, updated telemetry from space-based sensors, including data relayed through legacy Arecibo radar archives, fed directly into the simulations. Each new data point forced recalculations. Each recalculation exposed how thin the margin for certainty truly was. Quietly, another question hovered beneath the official language. What if this object behaved in a way we have never seen before? Interstellar visitors do not play by local rules. Their internal structure, thermal response, and long-term stability are guesses built on limited examples. Even Oumuamua, the most studied interstellar object before 3I Atlas, left scientists debating its nature years after it departed. Some proposed exotic shapes. Others suggested unusual ice compositions. None fully agreed. 3I Atlas was larger, brighter, and closer. As European drills progressed, coordination expanded beyond the continent. Data flowed between ESA, NASA's JPL, and independent academic teams at institutions like Stanford and Cambridge, each contributing models rooted in different assumptions. Some emphasized gravitational dynamics. Others focused on material science. A few examined whether internal cavities or volatile pockets could explain the observed behavior. Still, no single explanation satisfied everyone. And that is precisely why the drill continued, because planetary defense is not about predicting a single outcome. It is about proving that when certainty fails, coordination does not. By the time the exercise reached its midpoint, one conclusion had already emerged with clarity. Humanity does not lack technology. It lacks time. Detection, communication, decision-making, each step consumes precious days. 3I Atlas had compressed all of them into weeks. And as new data continued to arrive, one unresolved variable remained on every screen. Not where the object had been, not where it was, but how it might change next. For a brief window, everything comes together. Tracking data from the European Space Agency's Near-Earth Object Coordination Center, cross-checked with orbital solutions from NASA's Jet Propulsion Laboratory, confirms that 3I Atlas did not behave like a routine asteroid during its close approach. Its trajectory tightened faster than expected, its brightness spiked unevenly. Radar returns showed fragmentation patterns that did not match simple rotational breakup models. At the same time, observatories across Europe and beyond, including the European Southern Observatory in Chile and the Keck Observatory in Hawaii, reported rapid changes in the object's coma and tail structure. Instead of a smooth expansion, the dust cloud pulsed, brightened, collapsed, then expanded again. This is the moment when simulation rooms went quiet. Inside ESA's Planetary defense exercise, analysts ran worst-case scenarios. Not because impact was certain, but because uncertainty was suddenly too high to ignore. Computer models were fed live data from Gaia, archival Arecibo radar records, and thermal readings compared against James Webb Space Telescope infrared profiles. The result was not panic, it was urgency. 3I Atlas became the first real-world stress test of Europe's planetary defense systems. Civil protection agencies practiced cross-border communication. Space agencies rehearsed impact probability updates. Emergency planners tested how fast information could move from scientists to governments to the public without distortion. This was not about fear. It was about time. What emerged from the exercise was a sobering conclusion. Modern detection works, but response depends on coordination. An object does not need to be world-ending to disrupt satellites, aviation, power grids, or global confidence. Even a small uncertainty window can trigger large consequences. As Harvard's Smithsonian Center for Astrophysics researchers have warned for years, the real threat is not surprise, it is hesitation. When the drill ended, officials emphasized that no impact was imminent. But they also admitted something quietly important. 3I Atlas exposed gaps that only a real object could reveal. Gaps in data sharing speed, gaps in public communication, gaps between knowing something is out there and knowing what to do about it. The sky did not fall. But Europe moved faster than it ever has before, and that alone marks a turning point. If you want to stay ahead of discoveries like this and understand what scientists see before headlines explode, subscribe now and watch the next video on screen.